Okay, today we're going to have a major shift in the class. We just finished doing paracyclic reactions. So the 4 classes of paracyclic reactions, and the exam on Friday is going to be all about paracyclic stuff. And none of the stuff that we're talking about now will be on the exam. So we're going to start talking about kinetics. This is one of the premier features of this class, and if you go on to orals, advancement to candidacy exams, or leave graduate school, this is really one of the main components of your graduate education that everybody expects that you've had training in. So today we're going to start talking about rate equations. It's a really principal component of kinetics and understanding how to set up rate equations. And I want to just start off with a broader question: is why would you, if you're interested in doing organic synthesis, care about reaction kinetics? Of course, you care about which reactions work fast and which reactions are slow. And I want to take a simple example, because in this class, I continuously ask you on every problem set, on the exam questions, to suggest a plausible arrow-pushing mechanism for a reaction. And how do you decide what is plausible versus what is implausible? And it starts with you drawing some sort of intermediates out. You push some arrows around. So here's an example of an elimination reaction to generate a double bond here. And one plausible mechanism, if you're doing this in acid, is that you protonate the hydroxide in order to make that a leaving group. So that hydroxyl is now some sort of an oxonium ion. And so you can imagine that maybe the tosylate could pull this proton off and then push out the leaving group. Maybe that seems plausible. And so what does kinetics have to do with this? The idea behind kinetics is that kinetics is a tool for testing hypotheses. And so that's one reason that you would want to think about kinetics as a tool for testing mechanistic hypotheses. And I've drawn a mechanistic hypothesis up here. There's a second reason why you want to focus on kinetics and rate equations and stuff like that, and that is because it will allow you to make your reactions work better while you're in the lab running TLC plates, getting solvents ready, and we'll talk about that stuff later. Today I want to focus really on a more fundamental level of thinking about that. So one reason to think about kinetics is a tool for testing mechanistic hypotheses. So really, this is a mechanistic hypothesis, and what this is telling you, it's telling you that your reaction requires tosylate to pull this proton off at exactly the same time that the water is leaving. And if you believe that this is the slow step for the reaction, that has to be part of our hypothesis, that that's the rate determining step for the reaction, then what you're saying is that if you have 10 times more tosylate, your reaction had better be 10 times faster. If you add twice as much tosylate, if you go buy a bottle of sodium tosylate and scoop in some sodium tosylate into this reaction, your reaction had better be faster. And if it is not, then your hypothesis is wrong and you need to make a new one. It's that simple. And you're doing this kind of stuff in the lab all the time, scooping in more reagents, measuring out stuff. In other words, you have the chance to test your mechanistic hypotheses every time you're scooping something into your reaction or deciding not to. So that's very powerful. So the important part here about a kinetic picture of what's going on is it allows you to establish the concentration dependence of a reaction. That's what kinetics is for, or one of the main principles there. It's that concentration dependence. 10 times more should mean 10 times faster. So a kinetic picture of a reaction establishes the concentration dependence of the reaction rate, dependence of the reaction rate. And that makes it easy for you to test your ideas. Going back to the earliest days of organic chemistry, that's how kinetics was used. Okay, so let's talk about reactions. And I'm going to start off with a problem with chemistry, with language. And that is the term reaction is ambiguous. It's a term I use all the time. It's one of the words in the title of this course. If I just talk about some reaction in an abstract sense and I'm having some discussion, you don't really know what I'm talking about. So let me be less ambiguous. Let me be unambiguous here and describe 2 different types of reactions. And so one type is called an elementary reaction. We talked about this on the first day of class, that arrow pushing is most powerful when you use arrow pushing to represent the interaction of filled orbitals with unfilled orbitals in elementary reaction steps. And what distinguishes an elementary reaction is that they have one transition state, a single transition state. That's an elementary reaction process. Some sort of a process that has a single transition state. And I want to distinguish elementary reactions from composite processes, from composite reactions. Which have more than one transition state, where you go from A to B, but it involves multiple steps to go from starting material A to product B. Let's take an example of a composite reaction. How do you know when people are showing you something, or what's a good clue that they're showing you something that's a composite reaction? Well, most commonly, people put reagents and stuff above the arrows. So for example, let's suppose we put sodium T-butoxide above the arrow. Right? This is not what you do for an elementary process. For an elementary reaction, you usually like to have balanced equations. The second clue is you'll have things like solvents. And I don't know if you've noticed this, but every single time in the lecture notes I posted online, every single problem set, I give you temperature and time. Every single time I've ever shown you a reaction in print on our lecture notes that are posted online or on the exams, I give you the temperature and time because I want you to learn about kinetics. This has kinetic information in here. And you should pay attention to that. You should have been paying attention to that every single time I showed you a reaction. So there's kinetic information here. So this is a composite process. So at the end of this process, there's a new carbon-oxygen bond that wasn't there in the starting materials. There's a sodium cation. I'm not going to draw that. Okay, so you go from starting materials to products. There's a new carbon-oxygen, but something happened in there. And so this is a typical example of a composite reaction where there's lots of stuff going on. Let me try to break this down into something more fundamental. Let's draw out a mechanism for this. Right? What we said is that that arrow pushing has its greatest power when you use it to represent the interaction of filled orbitals with unfilled orbitals in elementary reaction steps. I think you guys know that boron is very electrophilic. Wants 8 electrons. It's a second row atom. So there's an empty p orbital on here that wants to be attacked. And so here's a very fast process that allows you to get an octet on boron. But now there's this kind of excess of charge. Boron is not really electronegative. Oxygen's electronegative. You know, really oxygen wants the electron. So you might not be surprised if there was some reversibility here. Maybe there is. That's part of our mechanistic hypothesis. And then in the next step, if I were really clever, I would draw an oxygen-oxygen bond here. And now what I'll do is, I know oxygen-oxygen bonds are weak. I'll take one of these boron-carbon bonds to the ethyl group, and I'll migrate that over and push out this T-butoxide and break that weak bond, the oxygen-oxygen bond. Those are easy to break. And so then I end up with this T-butoxide floating around. If I just push that out, so now I have this T-butoxide floating, and now I've got my ethyl group is now attached to oxygen. And of course, boron really wants 8 electrons. There's some resonance interaction here for the lone pairs nearby, but that alkoxide will want to attack. And that's how you get to the final product. I'll just write PDT here for product. Okay, so this would be an example of a plausible arrow pushing mechanism for this reaction. And the important thing is that I've broken this down into elementary reaction steps. Each of these steps represents an elementary reaction process, an elementary reaction step. So composite, and down here elementary. And I'm not going to write that above each of these arrows, but that was my intent, is to write, let me put a little line here so we can see. Each one of those steps represents an elementary reaction. Okay, now how do we avoid this language problem? Like when I say reaction, how do I get around this and clearly communicate what kind of reaction I'm talking about so I don't get lost in this jumble of elementary reaction, composite reaction, which I've never, a phrase I don't think I've ever used throughout this whole quarter. I'll show you the language that I use, and I'll just ask you to consider using this if you want to be very precise. Consider using the word step when you mean elementary reaction. There will be no confusion, right? Nobody's going to call this a step, right? That's a reaction with conditions. So consider using the word step to mean elementary reactions. That's what I've been trying to do throughout the whole quarter. And then when you want to talk about some reaction that involves reagents, times, temperatures, stuff you scoop into the reaction, maybe you should consider calling that a transformation, where you transform starting materials into products. It's just one way to try to reduce the confusion. And instead, I won't write temperature and time, I'll write with reaction conditions. In other words, I think it'll reduce the confusion if you refer to the transformations as those things that involve reaction conditions and reagents. Okay, so I'll try to do that while we're talking about kinetics. Okay, so let's think about the math that underlies these kinds of processes. And I'll come back to this oxidation reaction involving the T-butoxide. I want us to practice writing rate expressions and be good at it. And I'm going to start off with two different types. Well, there's really only two different types of elementary reactions. There's unimolecular, and there's bimolecular. So a unimolecular reaction means you've got some reactive intermediate that's just waiting to do something, to dissociate, to cyclize. Just one single component that's waiting around. Bimolecular reactions require a collision. They require some sort of a collision. Now, hypothetically, you could have termolecular reactions where three things have to collide simultaneously. We don't have any reactions like that in solution phase organic chemistry. It is so hard for two molecules to simultaneously collide with just the right orientation, just the right energy that you can make it over the energy barrier. It's so hard just to do this. There's no examples where three things simultaneously collide in a single transition state with just the right orientation. We don't have any examples. So you're not going to be writing anything other than these two types of elementary rate equations. So let's take some examples. Let's take an example of a unimolecular process. I'll write uni here. And I'll extract a couple of the steps from that mechanism that I drew. So one of the steps that I drew in that mechanism had this migration. I've got this weak bond here, oxygen-oxygen bond. I've got this borate. Really, this would be a boronate. So all these bonds to boron are electron-rich and nucleophilic. And so it's no surprise that these nucleophilic bonds here can push out the leaving group and really donate into sigma star and break this weak oxygen-oxygen bond. This is unimolecular. It doesn't require any collision of two molecules here. You're just sitting around waiting for this one molecule to do something. So this would be an example. And I'm going to try to draw a cursive lowercase k to represent a mathematical rate constant. That's a number that we can pin to that is measured in per second. It's like a frequency. 50 times a second, 30 times a second. How frequent is it for this ethyl group to migrate over? And you get these two products. So that would be an example of a unimolecular process. Let's take an example of a bimolecular step. I'll just write bi here. And that first step of the mechanism that I showed you was definitely bimolecular. You had a T-butoxide floating around. You had your triethyl borane. And that T-butoxide. And really, the arrow pushing here is not really relevant to this. We just want to get at the mathematical dependence here. I'm showing you the arrow pushing to try to make it more interesting, but really, if I ask you to write out some sort of a rate equation, arrow pushing is totally optional. That's for an arrow pushing mechanism. So I hope you can see here that this is definitely a bimolecular process. It requires some sort of a collision. If these collide 10 times faster, your reaction will be 10 times faster. If you have 10 times more T-butoxide, this will be 10 times faster. So let's write out the rate equations that make sense with that. How do we write out a rate equation that makes sense? Gee, it makes sense to me here that really the rate just depends on the concentration of this one species in solution. So running out of room here, but I'll try to write reaction rate equals some sort of a rate constant. That's this mathematical rate constant times the concentration of something, times the concentration of this boronate species that's in solution, where the T-butoxide, T-butyl hydroperoxide is attached to that boron atom. And there's a negative charge on boron. So that would be the rate expression. If I have 10 times more of this in solution, I'm going to be forming the product 10 times faster. That just makes sense to me. If I have 10 times less of this, how could I form this at any other rate other than 10 times slower? So that makes sense that there ought to be a linear correlation between the amount of this I have in solution and the rate at which I'm forming that product. Okay, and then on the bottom case, I've got two different components. If I have 10 times more T-butyl hydroperoxide, 10 times faster. If I have 10 times more triethyl borane, 10 times faster. If I have 10 times more of both, 100 times faster. And we write this differently. Now, what you're going to find when you do kinetics is that you'll oftentimes have more than one, you almost always have more than one rate constant. And we need something here to distinguish these. So usually you put subscripts here, sometimes numerical subscripts, like I could write 1 here and 2. The 1 and 2 have nothing to do with unimolecular and bimolecular. It's just some way for me to separate these, like R1 and R2. So I could write uni here, for example. Or I could write bi here, or I could write the number 2 here and 1 here, or 1 here and 2, or just something so I can distinguish them now that I've got two different rate constants on the board. So I'll write uni here for my unimolecular, and then I'll write a little subscript bi. And I've got two reagents, the hydroperoxide, and I'm sorry I've run out of room here, but the other species that I multiply here is the triethyl borane. Okay, so again, I hope this is intuitive, that you shouldn't have to set up a math equation, but if you need to, you can set up that math equation. Now, this rate constant is affected by the structure of my substrate here for this elementary reaction. If you want to change the rate constant, you have to change something about this. Change ethyl to phenyl. Change T-butoxy to some other hydroperoxy type leaving group. That rate constant K is dependent on the structure of this, and same goes for the lower case. If you want to affect K, changing the concentration is not going to affect that fundamental rate constant. The fundamental rate constant is dependent on the chemical structures of these. And oftentimes you don't get a chance to choose those. That's chosen by whatever reaction you're trying to perform in the lab. Okay, so I would expect you, for any simple elementary reaction type, there's only two types, for you to be able to set up a simple rate expression like that. And if you can do that, you've got kinetics under control. Okay, so let's switch to the more complex composite version, where we've got lots of things going on, some equilibria. How do we map this idea of an elementary rate equation onto a composite reaction? So composite reaction processes. I'm going to start off with I want to draw out a mechanism, a kinetic mechanism, where I'm trying to parse out rate constants and stuff like that. But any mechanism you draw is really a proposal. And so I want to write out one of the main features of any mechanism that you propose. If I ask you to write out a kinetic mechanism, what I really want you to do, first and foremost, before you do other stuff, is to include a rate determining step, or specify a rate determining step. And from now on, I'm just going to write RDS. So if you don't do that, if you don't hypothesize which of these steps you think is the slow step, then you haven't really drawn out a kinetic mechanism. So let's come back to my simple, I've got T-butyl hydroperoxide, I've got the triethyl borane, I've got some sort of a process here where maybe the T-butoxide comes in to make a boronate, or more specifically a peroxyboronate. And now my negative charge is on boron, which is not electronegative. Negative charge really wants to be on oxygen, so maybe it would go back, forth, back, forth. Maybe it would release the T-butoxide. And every once in a while, one of those ethyl groups will migrate over. And if I'm really drawing a kinetic mechanism, as opposed to an arrow-pushing mechanism, I have to specify which of these steps I believe is rate determining. And that would be this migration that pops out a T-butoxide anion and leaves you with this new carbon-oxygen bond. And then there's all this other stuff that happens after that. Well, in this case, not a lot of stuff happens after that. Really just the T-butoxide anion reattacks the boron. So you get this borate complex at the end. So this would be an example of a kinetic mechanism. Now I'm going to write rate constants here using lowercase, always these lowercase k's for rate constant. And I'm going to have more than one, so I'm going to start putting some subscripts here. I'm going to use italics lowercase k1 to represent the rate constant for attack of T-butyl hydroperoxide on this triethyl borane. And then for this reverse reaction, where the T-butyl hydroperoxide comes out, oftentimes we use -1 just to indicate that it's the reverse step. It corresponds to the reverse step for one of these other processes. That's very common. I need to use something here, and usually people just keep going with the numbers. The second step, they usually write 2. And again, this is supposed to be in italics, lowercase k. I'm not doing a good job of indicating italics here. And then there's this other stuff after the end. So let's make a few points about these. Actually, let me come over here. I would use K3 here and K-3 for these steps. If I had 4th and 5th steps, you could follow along and do the same thing. So when you set up, if I ask you to write out a kinetic mechanism, which is just a postulate for this, there's some things to keep in mind. Your rate determining step, if it really is the slowest step, you have to assume that it's going to be irreversible. In most cases. There will be a few cases where you're doing equilibrium reactions, but you're generally watching it go in one direction, forward or backwards. Forward, usually. Okay, so another thing to keep in mind. If this really is the slow step that's much slower than all the other steps by a factor of 10, it would be very unusual for the slow step to only be more favorable by a factor of 2 or 3. That would be very unusual. In 90% of cases, the slow step is at least 10 times slower than all of the other steps. And steps before the rate determining step are essentially in equilibrium. They're going back and forth, just waiting for some interesting thing to happen. So in 90% of all reactions, you've got this equilibration, back and forth, and every once in a while, the bonds are aligned just right in this intermediate for an ethyl group to migrate over and pop out the T-butyl hydroperoxide. That's most reactions that you will do, and that is most reactions that you will set up rate equations for. The important thing is that the steps after, or another important thing, is the steps after the rate determining step. and I'm not sure what language, I want to say not important. I'll just write, I want to say that. I'll simply say don't affect the rate. They teach you a lot about organic chemistry, but if you're just interested in rates and concentration dependence, forget them. They don't affect the rate of the reaction. It doesn't matter if there's 50 steps after the rate determining step. That's typically the case. They don't affect the rate of the reaction. So I arrive at my final sort of, or not semi-final, this is not the final, kinetic mechanism here. And that is this one elementary step. I want to focus all my attention on the one step that determines the rate of the reaction. And I'm going to set up a rate equation for that. I've got rate constant. It's an elementary reaction. I've got a rate constant. It's K2 times some concentration. And all I have to do here is look and see, is this unimolecular or bimolecular? It's unimolecular. So I just need one concentration. So I can express the rate of my reaction as the concentration of this species times a rate constant. And I'm almost done. I'm almost done with my kinetic mechanism, but there is one problem here. And the problem is, I have no way to measure this. The concentration will be too small to see by NMR. There's no type of spectroscopy you can do to quantify how much of that you have in solution. And so we're not quite done. The real goal of kinetics is to quantify, have some sort of a rate expression that expresses the rate of the reaction in terms of concentrations that you can measure. The amount of stuff you scoop into your flask or inject into your flask. And I haven't reduced this down to some, now I can kind of see, I think you can kind of see that if I put in 10 times more of this, I'll probably have 10 times more of this stuff floating around. I hope that's kind of obvious. If I had 10 times more triethylborane, I should have 10 times more of this species. There's this sort of intuition I would hope that you have. So we need to somehow change our math equation here to reflect this kind of obvious relationship that 10 times more T-butyl hydroperoxide ought to somehow give me 10 times more of this stuff floating around. And I don't know how much floating around, but there ought to be that relationship. So let's talk about this, because this, if this is the slow step and all this other stuff is fast, this is really an equilibrium. So let's talk about equilibria. There's this equilibrium that's going on here. I'm going to start by defining equilibrium. So what's the definition of equilibrium? It's got a simple definition. And that is that the forward rate of reaction is equal to the reverse rate. Starting materials go to products, products go back to starting materials. And those rates have to be equal or you're not in equilibrium. Let me go ahead and draw out an elementary reaction process, that first one, so we can talk about this equilibrium. And how do we define this? I'm kind of getting tired of this bornate thing, but I want to stick with the same example. That's my T-butyl group there. I'm just getting tired of writing T-butyl. Okay, so here's this bornate, and then this bornate goes on and does something. I don't really care about that right now. I just want to focus on this equilibrium. And this definition that says that the forward rate has to be equal to the reverse rate. And then there's this much slower thing that's at least 10 times slower than that, than these backward and forward things. That's the rate determining step. So if the rate forward is equal to the rate backwards, then we can express this mathematically. We can say K1, right? We can express the rate times concentration of these species for the starting materials, here's the rate expression, must be equal to the rate expression for the reverse rate, K minus 1 times release of T-butyl hydroperoxide, the rate at which this T-butyl hydroperoxide pops out and regenerates these two starting materials. And this is a unimolecular process. And this has to be true because the definition of equilibrium says, now remember, rate forward equals rate back is not saying that the rate constants are equal. Those under no, it's almost, it would be weird happenstance if the rate constants just happen to be identical. That's almost never the case. It's not the rate constants that are identical, it's the rates. Rate constant times concentration going forward equals rate constant times concentrations going backwards. Okay, so this makes sense to me. 10 times more of this means I'm going to have 10 times more of this stuff in solution. And this expresses that mathematically. So the important part here, if I rearrange this equation, what I would find, either profound or not, I think maybe you guys learned this at some point in freshman chemistry, or I don't know when. I think I learned this stuff in freshman chemistry, and then again when I took a physical organic class kind of like this in graduate school, and then I never used it again, sadly, because I didn't understand how to use it. If I just simply move all the concentrations to one side of the equation and all the rate constant stuff to the other side, I'll end up with an expression that ought to look pretty familiar, and that's products over reactants. Product concentrations over reactant concentrations. And it just so happens that that's going to equal the ratio of the rate constants. So I hope you all recognize this as your common equilibrium constant. And I'm going to use a capital K here in italics in bold. So the important point here is there's two different ways to calculate or express a rate constant. You can express it in terms of concentration, which are easily measured in the laboratory, or you can express it in terms of rate constants, not so easily measured in the laboratory, but very powerful for thinking about kinetics. Right? So in freshman chemistry, you express it like this because you can measure those things using UV vis spectroscopy or calculating how much you had at the beginning or the end. But when you start thinking about reaction kinetics, it's going to be often more useful for you to express equilibrium constants as a ratio of rate constants, because that gives us our intuition about which processes, which elementary reaction processes are fast, which are slow. Because those rate constants correlate with the interaction of filled orbitals and unfilled orbitals and charge and sterics, it's worth thinking about elementary rate constants. Okay, so that's our little spiel about equilibrium. Now let's go back to that that kinetic mechanism where we're trying to express the rate in terms of concentrations that we can measure. And I'm going to redraw this same thing that I keep drawing over and over again. So I've got this reversible combination of hydroperoxide anion and the borane to give this peroxyboronate. And then there's this slow rate-determining step that's much slower than this back and forth with the T-butyl hydroperoxide. This is my mechanistic hypothesis. And then one of the ethyl group migrates over and pops out. The T-butoxide anion. And then in some last step that doesn't have any influence whatsoever on the rate, so we don't care about that much, the T-butoxide attacks the boron to give me my final boronate, which could be in equilibrium with just the free boron compound and the T-butoxide. Okay, so let's just come back and let's write out the rate expression. and I'll be really picky here and I'll say, what kind of rate am I talking about? I'm not talking about product disappearance or starting material disappearance rate. I'm talking about product formation rate. Usually those are equal, not always. Sometimes starting material rapidly disappears and turns into some intermediate, and then it just sits around and slowly turns into the product. So it's not always true that the starting material disappearance rate is equal to the product formation rate. And I'm just being picky here. So remember that little elementary rate expression that's so easy to set up, but you end up with this concentration that you can't measure, and that's no good. And so the goal here is, how do we express this in terms of things that we can measure? And that's when we come back to this. I can rearrange this equation in order to express this in terms of some sort of constants and things I can measure. That's where this comes in handy, this expression here. And so let me, if I rearrange this math, and I'm not going to rearrange that equation for you. I'm just going to ask you to imagine what would happen if I substituted this with all this other stuff, these concentrations and those rate constants. And I'm convinced that you guys could do that. If I rearrange that math, what I would find is that this thing here is equal to K1 over K minus 1 times the concentration of something I throw into the reaction, and I can scoop right out of a bottle sodium T-butyl hydroperoxide anion and triethylborane, which I can also measure out of a bottle. So now I've reduced the rate expression into stuff that I control, how much I put into my reaction. And now I can test, was my hypothesis consistent with my kinetic mechanism? Right now I can ask, if I scoop in 10 times more T-butyl hydroperoxide, is my reaction 10 times faster? How do you know that? Look at your TLC plate. Look at the LCMS. You don't need to do anything fancy to tell if your reaction is going 10 times faster. You already know how to do that. You can test to see if your reaction gets 10 times faster when you add 10 times more triethylborane. Just inject 10 times more. You'll know right off the bat whether your mechanism was consistent. Now, there may be more than one type of mechanism that's consistent with this kinetic pattern. But this is very powerful, this idea that your kinetic expression, if I ask you to write a kinetic mechanism, I expect you to reduce things down into some sort of mathematical expression where rate is equal to some equation that involves measurable concentrations. And this is a testable hypothesis. You're obtaining this data all the time in the lab. Are your reactions getting slower or faster when you add more or less reagents? Okay, I want to come back to when you're in the lab. What are you actually seeing? What are you actually, if you actually go into the lab and quantify rate constants, and we'll talk about the units for those shortly, or maybe in the next lecture, I can't remember. But we'll talk about those units later. Okay, so let's go ahead and talk about what you measure when you go into the lab. So if you go into the lab and you run some sort of a reaction, you take a bottle of triethylborane, and T-butyl hydroperoxide, and you start measuring the concentrations of products over time, and you could prepare some sort of a plot, or do something to estimate the rate at which the reaction is occurring. What you'll end up with is some sort of a measured reaction rate that corresponds to this equation. If you assess the concentration dependence, what you would find is that 10 times more T-butyl hydroperoxide means 10 times faster. And you'd find that 10 times more triethylborane means 10 times faster. 10 times less triethylborane means 10 times slower. And if you plot it out, it would fit to some equation where where you required some sort of a constant to make everything work out. And this will or will not exactly match the mechanism that you proposed before. So let me distinguish what you measure in the lab with what you proposed, and how would you see whether those match? your kinetic mechanism had some sort of proposed rate dependence that looked like this. It had all this fancy stuff in there. And the reason I'm drawing this out is you might be frustrated. You might be frustrated by the fact that, well, how do I dissect K observed into these individual components? And most of the time, you cannot dissect this observed rate constant that you get down into these individual components. Maybe if you knew 2 of these, you could solve for the other one, but you frequently don't know 2 of those numbers. And you need to not be frustrated by the fact that you're never going to be able to figure out how this correlates with these other little rate constants in there. The important thing is that you got the concentration dependence right. That's usually what you're looking for when you work out rate equations and do kinetics in the laboratory. What you really care about is this a first order dependence? Twice as much, twice as fast. Half as much, half as fast. That's usually what you care about. And that's the main thing you're going after when you do kinetics in the laboratory. Okay, so again, usually you can't dissect K observed. Don't worry about it. Usually you're just looking to see if your concentration dependence matches that from your kinetic mechanism equation, for your rate equation. That's usually all you care about. And again, it's so easy to get a rough idea just by looking at your TLC plate. Sometimes your NMRs. We'll talk more about kinetic selectivity later. You get all kinds of information about whether your reactions are going faster or slower when you're in the lab. Okay, I want to come back and talk about, so I just told you that you can't really dissect K observed into these individual rate constants, but I want to talk about those individual rate constants for elementary reactions, because they can't be just anything. You want to be careful what you tell people about the rate constants for your reactions, the elementary rate constants, because people will be able to quickly decide whether they make sense or not. So the rate constants, that's not supposed to be bonds, that should be bounds, have practical limits. And I'd like you to know what those practical limits are. So at room temperature, let's take an example of some processes where that will allow us to talk about, we haven't talked about radical reactions. That's coming next. Let's talk about this process. There's ring strain here, and this system can respond to ring strain by popping open. So you get one of these electrons in this bond can combine with this radical to form a double bond there. This would be an example of a unimolecular process. So let's talk about the bounds of rate constants. So what kinds of bounds are there on K as to what K can be for a unimolecular reaction? So typically what you'll find, I'll put the rate constant for an elementary process here. Let me draw one here to represent unimolecular. So what you'll find is that no rate constant for a unimolecular reaction can be faster than a fundamental limit. And that fundamental limit is about 10 to the 13th per second. There's no concentration dependence to this. It doesn't matter what the concentration, you're just limited here by how fast these things pop open. If it takes an hour for the reaction to complete, putting 10 times more stuff in there, it'll still take an hour for it to complete. One molecule in there doesn't have any influence on how fast the other molecule is popping open. So this would be the practical limit. And the reason this practical limit exists is that's the rate, approximately, for a bond vibration. You look in your IR spectrum, you can see stretches in there for CC bonds. And this corresponds to the frequency of CC, CN, CH, within factors of 2 or 3. And we're interested in factors of 2 or 3, not factors of, we're not interested in factors of 2 or 3. We're interested, when we look at this, in these sort of exponential numbers. So this is the speed limit, and it's a fundamental limit set by the rate of bond vibration. Why is bond vibration a speed limit? Because the mechanism for bond cleavage has to do with the rate of vibration of this bond. The bond pops open by vibrating. When it vibrates really far, it pops open. And there's no way to pop open faster than you vibrate. So that's why this sets the upper limit. If somebody tells you they've got a rate constant that's 10 to the 15th, something is wrong. Right? Maybe they were in another universe, or maybe they were heating things to 6 million degrees or something. Something was wrong right there. So you have to be careful of that. And you don't want to be the person who claims that your rate constant is larger than this at room temperature. Now, what's the lower limit? And I just made up this lower limit. If somebody tells you that they went into the lab and ran some, that's supposed to be a minus, sorry, and they measured some sort of elementary rate constant that's below 10 to the minus 8, we're talking years. How did they do that? Right? You do not care about any reaction that is slower, that has a rate constant slower than this, because you don't have that much time in graduate school, you don't have that much time in the lab, you don't have that much time on a federally funded grant project. It's just not meaningful to talk about processes that have rates slower than this at room temperature. It's not meaningful. And of course, this is kind of soft, right? You could argue, well, it's not even meaningful if it takes 8 months, right? It doesn't have to be years. Somewhere around this range of 10 to the minus 7, 10 to the minus 8, you're starting to talk about time limits that are just not practical. Okay, now let's take a look at bimolecular processes. What sets the limit on the rates of bimolecular reactions? And so I'll take as an example, and I'm sorry, I'm running out of room here, so let me come to this other board. What sets the speed limit on bimolecular processes? And I'll draw out an example of a bimolecular reaction. There's a stabilized radical, an allyl radical. It doesn't matter how stabilized this radical, well, maybe it does matter a little bit. The bottom line is when carbon doesn't have an octet, it's really angry. And so you can expect radicals, second row radicals, to combine very quickly in almost all circumstances. And in this particular case, this recombines, let me put this with K2, with a very fast rate constant. So let me come back over to here. I picked this reaction because this reaction has a rate constant of about 10 to the 13th per second. This is one of the few reactions in organic chemistry that I just happen to know. Right? You should take the time, whenever you see things that operate this quickly, to take note of them. Very few things are so fast that they react at the level of a bond vibration. And so that's about 10 to the 13th times per second. And I'm giving you an example here of another process that's so fast that it also is bounded. Notice that the units change. Now it's per molar per second. Now there's a concentration dependence. It actually matters how much of this stuff is in solution for how fast you form bonds. And let's talk about the limit of rate constants for bimolecular reactions. So this would be our second case. And if we measure the rate constants for bimolecular reactions, what would we expect? And since I drew a 2 there, I'll use a subscript 2. So now the bounds are not bond vibration. That would be great if it was. But this is kind of the upper limit, 10 to the 9th per molar per second. And this is the rate of diffusion. When you have bimolecular processes, you are limited by the rate at which two molecules can diffuse and find each other in solution. There is no way, if two molecules are on the opposite side of your flask, that they're suddenly going to form a bond. You have to wait for them to randomly collide and diffuse towards each other, and before they can form a bond. And so that corresponds really an upper limit on rate of diffusion. Now sometimes you'll see people say 10 to the 8th. Why would it be different? Why 10 to the minus 9 versus 10 to the 8th? It has to do with solvent viscosity. If you've worked with ether in the lab and you've worked with water, you know water is more viscous than ether. Ether is very light and flows very freely. So a biochemist would probably use 10 to the 8th per molar per second. Viscous aqueous solutions with high salt content. Whereas an organic chemist working in a non-viscous solvent could have rate constants that are approaching that kind of a level. And again, the bimolecular rate constants, it really doesn't matter whether you're talking about 10 to the minus 9 or quibbling about 10 to the minus 9, 10 to the minus 8. Somewhere around here, you're starting to talk about the year-long time scale again. And if people start talking about their reaction that has a 10 to the minus 12 rate constant, something's wrong. Right? They did something to get that number. They extrapolated. Right? When you start talking about reactions that take years, that's not realistic. Okay, I'm going to go ahead and stop there. We're not quite finished talking about rate constants. And when we come back on Wednesday, I want to talk about where can you get this kind of information? How can you look up these values, or how can you know these values ahead of time without walking into the lab and making measurements? And there's some places you can go to get that information.